here I want to go and think for just a moment about one of the most famous album covers of all time. I am, of course, referring to Pink Floyd, The Dark Side of the Moon. Now, if you have the vinyl in the two album set, you will see on the inside cover, you'll see that they have two prisms kind of arranged sort of like this. There we go. And in it, you see light coming in to the first prism, a fairly steep angle, actually, something like this. Coming in the first prism, it refracts through the second prism and then comes out the third prism and heads over. Now, coming out, though, you notice that it's no longer just pure white light, but you've got this spread of colors here. You've got the blues up here and the reds down here, and then they pass it through the next prism. Now, this is a bit of an homage to an experiment due to Isaac Newton. There was a lot of debate in the early days of optics about the nature of color. The question was whether the two camps basically came down to was what we accept as the current model was white light, the combination of all the colors of light, which is what we currently accept, or was it the case that color kind of got added on to white light? And honestly, you could make a good argument either way. For instance, if you think about, light passing through a stained glass window, the arguments seemed pretty compelling either way, that either somehow the stained glass window was just adding a tint to the light somehow, or it was the case that the stained glass window was absorbing all the colors except what was passing through it. So Newton figured that he would try to suss this one out. So here, if we go and let's redraw this middle ray here, this middle ray being in the middle of the spectrum is now green. And what he did was he put a partition right here that blocked everything. That blocked everything except the green light. And he tried this with all sorts of other colors too. It wasn't just green. And then what happened was as you passed through the second prism, you just had the green light. You just had the green light continuing on through. Like so. And there were no additional colors. So with this, Newton was able to argue that the prism wasn't adding, when the prism was making the pretty rainbows, it wasn't adding color to the light. Because if that was the case, then after you blocked this out and passed just a single color through, you should do the same thing. You should spread it out and add colors. But that's not what happened. Just that one lone color passed through. And so from that, Newton was able to demonstrate that white light was the presence of all colors of light. Now, what's going on with this? Why does this happen? the phenomenon is called dispersion, and we can get another look at it with this photo right here. You can see that the blue light in the photo is bending more strongly away from the normal than the red light is. Now, what's up with that? This turns out to be a general property of materials. If you plot the index of refraction of a material as a function of wavelength, what you find is that's not a constant, but it actually decreases with increasing wavelength, or here, as wavelength decreases, the index of refraction would increase. Now, it does turn out that every so often, as you go from one frequency band to another, there's sort of a funky mechanism by which this function resets itself, and you kind of hop back up very quickly and then decay back down. But that is way beyond the scope of our treatment here. In the visible, pretty much every material that you'll look at in the visible will behave like this. So let's think about this from a Snell's law perspective. If I shine white light in, which is a combination of all the colors, so that's just going to be N1 sine theta 1, that's going to equal N2 sine theta 2. Now, what we see here is that for blue light, so blue light is shorter wavelengths and red light is longer wavelengths. For blue light, the wavelength is dropping down. And that means that the index of refraction is higher than it would be, say, for red. But it still has to be the product of N2 and sine theta 2 has to be the same regardless of whether we're talking red or blue. So for blue, N2 is higher. That makes theta 2 have to go down. So the moral of the story here is that blue bends better. So it will... Violet bends best, but that doesn't alliterate. So going from a from a low index to a high index, blue light will bend more strongly towards the normal. And going from a high index to a low index, which is what you saw in the photo, blue light will bend more strongly away from the photo. Oh, sorry, away from the normal. Okay. So this is a good opportunity to discuss what's happening when you look at a rainbow. So if you ever notice, whenever you look at a rainbow, the sun is always to your back. And the big scary storm cloud is over there, dropping its rain down. So it turns out that if you look carefully at how light travels through a drop of water, so we have white light coming in from the sun, following our maximum here. Here's our first normal that we need to strike. The blues will do a better job of bending than the reds. So the blue light will do something about like that. There we go. About like that. While the reds will do something, come on. There we go. About like that. Now here, some light will pass through, but it turns out that for the angles involved, there's an awful lot of internal reflection. So the light here will get internally reflected, like so. And the red light will actually cross the blue light because it internally reflected off of a different location. So something like that. And then when we get out here, so again, we'll drop in our normals. The blue light is going to do a better job of bending away from the normal than the red. There. And so if you look at this combination of reflections and refractions and reflections, what you get is the angle that's made between the incident white light and the blue that backscatters out of the drop. That turns out to be 40.8 degrees. And to the red, turns out to be 42.5 degrees, roughly. So when we look at the light coming in from the sun, oops, there we go. It'll say hit some random raindrop, like let's say that one right there. And the blue light will have a combination of reflections and refractions. If it's up this high, it's actually going to miss your head high. But the red light will make it to your eye. So when you look here, you see red. Now, if we go look at some parallel ray of light that strikes a little lower, because remember, the sun is so far away, the rays of light are effectively parallel. There we go. Again, it hits some random raindrop like so. And again, it'll be the same deal, except here, it's going to be the blue light that's scattered into your eye. And the red light is going to miss your eye. So when you look here, what you're going to see is the blue part of the spectrum. And then in between, there will be some, will be the colors of the rainbow in wavelength order. Because remember here, as we go to ever shorter wavelengths, the index of refraction is going up. And oh, by the way, if you're wondering in tables when they quote the indices of refraction, if they don't specify it, if they don't say what they're quoting it for, it's for a certain particular wavelength of green light, which is in the middle of the spectrum. So there's some orange for you, and some green, and then some yellow. Wait. Roy G. Biv. Nope, sorry. There's some yellow for you. Then there's some green for you. And then we could go down and do indigo and violet if you feel so inclined. So sure, let's put in some violet down there. So perhaps not as entertaining as what say the what Germanic peoples held to, which was that the rainbow is the bridge that connected the battlefield to Valhalla, and that the red on top of the rainbow was living fire that only the Valkyries could successfully transit without dying, as they took the bodies, as they took slain soldiers up to Valhalla, where there was basically more feasting and more beating of each other up until the day of Ragnarok, when absolutely everything got destroyed, including the gods, and replaced with something better, but we didn't know what. But I still think this is pretty cool too. Just to know that the light is coming in, and you have two refractions and one reflection bringing it back out. And by the way, for the double rainbow, that happens because there's yet another internal reflection before you get your refraction out.